Great, thanks. Yeah, so the genesis of this talk was, again, I've been doing this for a long time. When I started in the industry, I still had hair. The genesis of this talk was my realizing that every time I made some aspect of some architecture more scalable, what we were really doing was making it simpler. And we were making it simpler on at least one of many dimensions. And so what I want to talk about is the unreasonable effectiveness of like making simple changes, making the systems, individual components of the system simpler. And then the complexity of the system is around composing those small individual simple components together in interesting and complicated ways. Actually, most recently, I was VP of Engineering and Chief Architect at eBay. I left a couple of months ago, but that was my last thing, and when I'll talk about a bunch of stuff from eBay here today. I also spent a bunch of time at eBay earlier in my career as well as an individual contributor. I spent some time at Google running engineering for Google App Engine, so that's Google's platform as a service, like Heroku or Engine Yard or Cloud Foundry, something like that. I led engineering at Stitch Fix, which is a clothing retailer in the United States with a ton of data science and machine learning, up to and through Stitch Fix's IPO. And then after that, I also worked for several years at WeWork, up to its not IPO. Okay. So I want to tell two architecture stories, and apologies to people who saw these yesterday, but I love these stories so much I'm going to tell them again. eBay, depending on how you count, is on its fifth complete rewrite of its infrastructure. So it started famously 27 years ago in 1995 with the founder, Pierre Omidyar, in a 3-day Labor Day weekend, was playing around with this new cool thing called the web, and he built the first thing that ultimately later became eBay. And it was a monolithic application, all written in Perl. Every item was a file that lived on, I like to imagine, his 386 tower that sat under his desk in Redwood City, California. It didn't scale, but of course it wasn't meant to. The next iteration of eBay, which they cleverly called V2, was a monolithic C++ ISAPI DLL. So it was a DLL that plugged into Microsoft Internet Information Server and written in C++, like I mentioned. It grew at its worst to be 3.4 million lines of code in that single DLL. The team was hitting compiler limits on the number of methods per class, which I'm embarrassed to tell you that I remember what it was. It was, the Microsoft compiler at the time was 16K methods per class. So they were hitting that limit. You can imagine what a horrible situation that was to work in. They weren't just all in the same repo. They weren't just all in the same file. They were actually all in the same class. So you can imagine all the developers stepping on each other's toes in there. The next iteration was cleverly called V3. And that wasn't yet microservices, but that was sort of Java mini applications. So for each part of the site, there'd be an application that would serve, the search part of the site, the selling part of the site, the buying part of the site, the payments part of the site, et cetera, times about 220 different of those applications, the sum total of which was eBay. And then there was a subsequent iteration leveraging Spring, and then a subsequent iteration leveraging Spring Boot. And now I think it's fair to characterize eBay as a polyglot set of microservices, mostly written in Java, but a bunch in Node.js. Amazon has gone through a similar evolution. So it started almost exactly the same time as eBay in around 1994, 1995 timeline. Its original monolith was codenamed Obidos, and it was a monolithic Perl and Mason front end over a C back end. And it was a 4 gigabyte application in a 4 gigabyte address space. So it was pretty memory constrained. You can imagine even just swapping memory in and out to keep the application in memory. They were regularly breaking the GNU linker, trying to just build this application all at once. And it was so, we'll say, effective at leaking memory that they ended up having to restart the server every 100 to 200 requests. Because of the memory leaks. As a consequence of, again, everybody being in this same monolith, Amazon was releasing about once a quarter. So this was pretty bad. The brilliance and the kind of investment that Amazon made after that was in fully migrating from that monolith into what we would now call microservices, what they were then calling just a service-oriented architecture. And those services were written in the more modern languages of the time, so C++ and Java. And there was absolutely no sharing of data, between those applications. And then, again, in case anybody thinks that, like, architecture doesn't matter or these things, don't have impact. You can, just a year after they finished that service migration was, AWS starts launching with its first set of services, and Amazon starts its, inexorable takeover of the world's online retail. So architecture really matters, and in particular, the service-oriented architecture really enabled Amazon to hockey stick their growth. So what we can learn from these is that no one starts with microservices, but past a certain scale, almost everybody ends up with microservices. So let's talk about what it means to be in a microservice environment, like at really large scale, at the eBay or Amazon or Google or Netflix scale. And I want to talk about 4 different elements here today, all aspects of simplicity. So first, I want to talk about some architectural kind of building blocks that we use at large scale. So I want to talk about simple components, and then I want to talk about simple interactions between those components. Then we'll take a little bit of a step to the side or expand the idea here and talk about development practices that allow large-scale systems to make really simple changes and do them safely and repeatably and reliably. And then I want to put everything all together, put those architectural building blocks together, and build some interesting things and talk about and show some particular case studies that are interesting and illustrate some of the points. Okay, so let's start with simple components. So the first of those components is modular services, right? So again, both of the examples that I gave are service-oriented architectures, and those service boundaries that bound, the services around selling from the services around search, et cetera, those are matching the problem domain, and each one of those services, is kind of directly implementing some part of the business logic that's associated with that problem domain. And those service boundaries are encapsulating both business logic and data. So all the interactions that we want are through that published service interface, and the interface is hiding the internal implementation details, and there aren't any backdoor ways to get in and out of the data storage. So everything is coming through the front door through that published service interface. And these service boundaries are kind of encapsulating what I'll call architecturalilities, right? So these service boundaries encapsulate fault isolation. They're a performance optimization boundary, like it allows us to do caching and performance improvements kind of within the service boundary. And also super critical in the modern world is that they're also a security and a compliance boundary as well. So within those services, we also want to make sure that the domain logic is nice and orthogonal from the non-domain concerns in there. So in the best services that I've worked on and worked with, the domain logic is implemented in a stateless way. So ideally, it's a stateless pure function that just takes a bunch of inputs, does a bunch of processing, and produces some outputs at the end. If we build domain logic in this very stateless way, it ends up giving us this ability to match the domain problem very directly, like there's no non-domain stuff in that stateless pure function. It also, as we'll talk about a little bit later, it also, that if we can develop it that way, it also makes it deterministic and makes that logic testable in isolation and a lot more easily testable because, again, that domain logic is separated from the other concerns. And then also, because that domain logic is written very clearly and very cleanly, it ends up being more robust to change over time. Like it turns out that the domains change a lot less than the technology and the frameworks that we use. And the way I like to think about the implementation of one of these things is that we implement the domain logic in a very straight line way. So very straightforward, very synchronous internally, and with minimal branching. And again, this allows it to be very straightforward, but it allows also us to leverage modern chipsets and cache hierarchies and so on. And so the critical idea here is to separate the domain logic from the other aspects, so from the I/O aspects, right? So people are probably familiar with hexagonal architecture, or maybe people have heard of the ports and adapters pattern. Like that's what we're talking about here, where again the domain logic is this one kind of orthogonal part, and then everything else, all the side effects, are kind of around that. And the other way to think about it is this is functional core with an imperative shell. The next thing I want to talk about here is sharding. So, services allow us to kind of vertically, chop up our overall problem space, and sharding allows us to kind of chop it up in the z-axis or in the depth direction. So shards are about partitioning the services, what I'll call data space. So they're a unit they're a unit of distribution, they're a unit of replication, they're a unit of processing, and a unit of storage. And usually in the modern world, these are hidden as an implementation detail, but they're definitely there at large scale. And these shards are also encapsulating different architecturalities, right? So they encapsulate a resource isolation. They're also a fault isolation boundary. They encapsulate availability concerns and also performance concerns. And then also, again, in the modern world, those shards are typically auto-scaled, right? So we're going to divide or scale out those shards as we need more and more processing, or we have more and more data to process. And some examples here from DynamoDB and Aurora and Bigtable are all examples of how large-scale systems are built on these individual shards. So the next thing I want to talk about is that services are layered. So we'll start with the kind of like customer-facing services at the top, and then we'll have common services that provide and abstract out widely used capabilities that are leveraged by a bunch of different customer-facing services. And then at large scale, these services represent actually an ecosystem where services call other services, which in turn call other services. And it's really more of a computational graph than a layer, but I like the term layering. I think it makes sense there. And these services are going to grow and evolve over time, right? So over time, we're going to factor out common libraries and common services as we find we need them. Actually, what I've noticed in these service ecosystems is that teams and services actually end up splitting, kind of like cellular mitosis, right? So you start with one cell or one service or one team, and it splits into two daughter teams or services, and that splits and so on, kind of like biological, biology. And then the other thing I want to talk about here is leveraging a common platform. So again, at large scale, almost all the effective places are building this common platform and giving kind of a paved road to the developers on which to build their services. And that common platform is going to encapsulate shared infrastructure. It's going to provide standard development frameworks. It's going to provide standard aspects of the developer experience, like version control and CI/CD pipelines and build and test and deploy and all that kind of stuff. And then Netflix and Google are really good examples of this. The other thing, and what the common platform allows, is a separation of concerns from the individual service teams to be able to build and maintain their domain level service, and it reduces their cognitive load and allows them to kind of bound the decisions that they're needing to make through enabling constraints that come from the platform. So interestingly, at these large-scale organizations, because there's so much ROI in terms of these investments, a lot of these large-scale organizations invest more than 50% of their engineering effort in these platform capabilities. And if you're a smaller company and you're leveraging cloud services, you might look at your overall engineering and operational expense, and you're probably spending 50% as well. And then these services evolve over time. And so, when I was at Google, what we found is that there was a lot of variation, sort of, again, like biology, like variation in natural selection. So we were constantly creating and extracting new services as we found those needs. Services would justify their continued existence by continuing to be used. And then we would deprecate services when they were no longer being used by anybody. And again, as we mentioned, domains are going to grow and divide over time. And so there was enough, I'll call it churn in the Google ecosystem that we always had this fun thing we like to say, that it always felt like every service at Google was either deprecated or not ready yet. OK. So that was talking about simple components. Now I want to talk about simple interactions between the components. And the first one of those interactions I want to talk about is an event-driven model. So in this situation, rather than synchronously communicating, we want to communicate state changes between service A and service B as a stream of events. And so an event is a statement that something interesting has occurred. Ideally, it represents something that's semantic part of our domain. And the reason why we do these event-driven things at large scale is because it helps us to decouple domains and teams from each other. It allows them to be abstracted away through the well-defined interface of the event, and it allows them to be asynchronous from each other. And also, interestingly, if our mental model is we receive an event and we do some processing and then we produce an event, that's actually a really simple component model, or a simple implementation model, and it actually simplifies in a lot of ways the component implementation that we have to do as a service team. And events are so important that the way I like to think about it is that they're actually a first-class part of the service interface. So, a service interface, in my view, includes not just the kind of obvious synchronous request response through the front door, whether through REST or JSON or gRPC or something like that, but it also includes all the events that the service produces. It includes all the events that the service consumes, and it also, we won't talk about this, but it also includes any other kind of bulk reads and writes that we might do into or out of an analytic system. And so the way I like to think about it is an event interface includes any mechanism that covers any mechanism that gets data into or out of the service. So the next thing I want to talk about here is storing our data inside our service as an immutable log. So this has a lot of advantages if we store state as an immutable log of events that we've accumulated. And often, as we'll talk about in just a moment, actually this way of thinking about the capabilities of the service actually very directly matches the problem domain. The reason why we do this is, again, the log encapsulates a bunch of architecturalilities that we care about, right? So the log represents the durability of the data that we're storing. It allows the changes that we've made to be traceable and auditable. It also allows us, if we need to replay events from before. And also from a debugging perspective, as a developer, it makes it really, to have a kind of log of events that we've consumed. It makes it very explicit and very comprehensible what's actually happened. And so being able to reconstruct what happened to get us to maybe this weird state is a lot easier in a situation where we've stored things as an immutable log of events. And then, as you can imagine, if you just continue to, build the log up, forever, that's not going to work. And so, a standard technique is that we compact the log every so often for efficiency, and so we can continue to kind of keep the size of the log constant over time, even though we're adding more and more data over time. And so, the quick example of how an immutable log can very directly match a domain comes from Stitch Fix. So Stitch Fix, as I mentioned, is a clothing retailer in the United States. And so a thing we would do, or the main thing we would do, is we would send boxes of clothes to our clients. And so the details here aren't super important, but the way that we modeled the order processing and the package processing and the delivery processing was as a series of these immutable events. And we would just continue to append new events to this log. So somebody requests an order, and then we assign that order to a warehouse, and then it gets what we called styled, where somebody would decide what clothes would go into that order. We'd walk through the warehouse and pick those items. We'd pack the items. We would ship them. They would travel over snail mail to the customer. Then the customer would receive them. Anyway, so this whole modeling this domain as a series of immutable events was really very natural and really gave us a lot of advantage. The other thing, of course, is to embrace the asynchrony between the services, right? So if we have an event-driven connection between the services, we should be able to leverage asynchrony there. And what that allows us to do is decouple the operations that happen in service A from the operations in service B in time. So it allows us to decouple the availability of the service, like A can be up when B is down, B can be up when A is down, everything still works correctly. We can independently scale service A and B from each other. It allows the services that consume the events to do potentially longer running processing, more complex processing, more expensive processing than we'd be willing to do while the customer is like waiting for us to get back to them on the web page. And then also, because there's this separation in time and in space, it's safer to make independent changes to the separate services from each other. And again, just like event-driven in general, this model actually also simplifies the component implementation in a lot of ways. And so one of the things that we'll talk about later on when we go through some of the case studies is now we have this really powerful ability to potentially invert a synchronous call graph into an asynchronous data flow. So like you can imagine that you could start with something, and I'll give this example later, where A is calling B is calling C is calling D, and when we do that synchronously, there's a lot of anything that goes wrong is going to impact the customer experience. Whereas if we can invert that and we have D produce events that are then consumed by C, which produces events that are consumed by B, which produces events that are consumed by A. That actually is a lot more robust to change over time and a lot more resilient to potential failures. And so we'll give some examples later that are pretty interesting. Okay, so we talked about simple components and we talked about simple interactions. Now I want to kind of take a sidebar and talk about simple changes. The first idea here at large scale is that we want to make sure that every change we make is as small as it possibly can be. So this is the simplicity aspect of changes. So every large change that we want to make, we want to decompose into small incremental steps that are much more manageable. We want to make sure that each one of those steps is maintaining both backward and forward compatibility of data and interfaces, because as we make these individual changes, we don't want to break anybody else who's relying on our service interface to do their work. And then as a consequence, at large scale, multiple versions of a single service are actually commonly coexisting in production. So almost every change that we're making is a rolling upgrade from version 17 to version 18, something like that. And it's much more common at these large scales to have transitional states be the norm rather than the exception. So it's way more common to look out over the system and see for any individual service multiple versions rather than more common thinking that it's more common that there would be just one. So if I can expand slightly the idea of architecture, I want to talk a little bit about development practices that are important at large scale, and then we'll get back to the main architecture stuff. So to me, what's one of the most important aspects of an architecture and a software system at large scale is that we get feedback, and that we get feedback really rapidly and really high quality. And so the investment that we make in automated testing is critical, and as we get larger in scale, that investment is even more important than at small scale. And why do we do this? It's not to slow ourselves down. It's because tests actually allow us to go faster. Tests are the solid ground that allow us to move really, really quickly, and tests are the safety net that allow us to catch ourselves when something goes wrong. Tests help us to make better code because it gives us the confidence to potentially break things and refactor in a merciless way. And tests also help us to make better systems because it allows us to catch bugs earlier and fail faster. It also improves developer productivity. So in 2006 at Microsoft, they did a study about what do developers actually do all day, and it turns out that it's not what we expect. It turns out that developers spend 75% of their time reading existing code, 20% of their time modifying that existing code, and actually only about 5% of the time writing new code. Your mileage may vary, but like this seems pretty accurate to me actually when I actually observe what I do. It turns out that a major investment in tests help improve the vast majority of the stuff that developers are doing every day, right? So how does it improve reading existing code? Well, tests are like executable documentation that tell us how the system works. And so that really helps us to kind of read and understand the existing code. Obviously, the existing tests help us to modify the existing code. That's one of the reasons why we wrote it. And it turns out actually also that tests help us to write new code because tests help us to make better designs. As we make our code more testable, It turns out that what does more testable mean? It means it's more modular. It means it has better separation of concerns. It means it has more abstraction, back to all those things back to Dave Farley's keynote that opened up the conference yesterday. So it turns out that as we invest in testing and we make our, we then force ourselves to make our code more testable, it actually makes our designs a lot better and produces better results. But don't believe me, believe Michael Feathers, who's the author of Working Effectively with Legacy Code, one of the best books of software development, and actually the only book that was required reading when you joined Google. So as Michael Feathers says, there's a deep synergy between testability and good design, and all the pain that we feel when we write unit tests are pointing at underlying design problems. So in my experience, the best place the place that sort of epitomized the value of test-driven development was when I worked at this company, Stitch Fix. And they had been doing test-driven development for quite a long time. And as a consequence, there basically was no bug tracking system. I mean, we would produce bugs. We were just as good at producing bugs as anybody else on the planet. But we basically were able to have a kind of inbox zero model for bugs. Every time we saw a bug in production, we would write a test to validate the bug, and that test would verify the fix that we made. And then as a consequence, we would just always be fixed. When a new production bug came up, we would just fix that bug. And unlike every other place that I've worked in my long career in the software development, we did not have a big long list of, big backlog of hundreds or thousands of bugs that we found and we're never going to fix. That we were always able to kind of stay inbox zero. So this is the kind of advantage you can get by investing in test-driven development. So the other obvious thing that we need at large scale is canary deployments. So the idea is that we're not going to deploy in one big chunk to the entire fleet of machines. Instead, we're going to go slowly at first. We're going to monitor the metrics, both business and operational, and we're going to then go faster and faster as we gain confidence. So a canary deployment capability allows us to we're automatically monitoring changes to metrics. If those metrics are good, we're going to be able to continue moving forward. If the metrics are bad, then we'll automatically roll back. And the goal here is to make deployments routine and absolutely boring. The other technique here is feature flags. So again, that's a configuration flag to enable or disable a feature for a particular set of users. Just like with canary deployments and these other techniques, this allows us to build and maintain much more solid systems because it helps us decouple feature releases from code releases. It allows us to rapidly turn things on and off without anything else involved. And it gives us the capability to kind of develop and build and test and verify our software in production. So if we sum all these things up, we have continuous delivery. And so each of those individual services at large scale, we want to be deploying, or at least have the ability to deploy multiple times a day. So we have this robust build, test, and deploy pipeline at these large scale companies. We're monitoring our service level objectives to make sure that everything is going well. And then again, this allows us to build much more solid systems because we release smaller, simpler units of work. Again, the changes are simpler. We're getting fast feedback from the testing and from the build and deployment pipelines and from the canary deployments. It allows us it's faster to repair issues that we find. It's easier to understand those potential changes that we're making, and it allows us to increase the rate of change to our system while at the same time reducing the risk of that change. So very briefly, what I came back to eBay to do about 2.5 years ago was introduce these kind of continuous delivery capabilities to the company. Again, eBay's been around for a long time, and so I led this cross-company we called it a velocity initiative to improve software delivery. And our idea was to, again, think big, start small, but learn fast. So we iteratively identified a whole bunch of bottlenecks and issues that teams were running into in terms of building and testing and deploying, and we would ask the teams, what would it take for you to deploy your application every day? We would get a big long list of things from them, and because I also led the platform team, I could say, great, you just gave us our backlog. The results I'm pretty proud of. So we actually were able to double the engineering productivity of the teams that we worked on. We definitely moved the deployment frequency and lead time metrics from the Accelerate book pretty substantially. And even though we weren't focused on the failure metrics, we also substantially improved the failure metrics as well. One of the reasons I bring this up because we wanted to make a lot of large-scale architecture changes to eBay, but the prerequisite for making those large-scale architecture changes, and one of the indicators of a really good architecture, is being able to make small changes rapidly and safely and repeatably. And so was it worth it for us to invest in these things in order to be able to do make our large-scale architecture changes. And because I can't help myself, I will refer to one of my favorite books, the Accelerate book here. So this summarizes the state of DevOps research from now 9 years. And if you in the large-scale companies that have adopted these capabilities, spend 44% more of their time on features versus maintenance, and they actually are 2.5 more times more likely to exceed their goals, business goals around profitability and market share and productivity. So this stuff really matters. Okay. So now we talked about simple components. We talked about simple interactions between those components. And then we took a sidebar to talk about kind of the development practices around being able to make simple changes to the system. So now let's put things all together. So at large scale, one of the critical aspects in a service infrastructure is that we only have one system of record for any particular piece of data, right? So any particular piece of data is owned by one and only one service, even though we have maybe hundreds or thousands of them. And that service is the system of record. Every other copy of that data is a read-only, non-authoritative cache, and all those words matter, right? So it's read-only. If I update, the customer record in some other place, it doesn't, correctly, it doesn't flow back to the customer service. It's non-authoritative, so I might ask somebody else about what the state of the customer is, but that could potentially be stale. So I want to talk about, give some generic examples of how we would solve some of these problems with services and these common problems with services and events, and then I'll give some case studies and we can have some questions. So how do we deal with shared data in one of these large ecosystems? So one way of getting data is just simply synchronously calling the service, right? So in this example, maybe we want to ship a package to somebody. The fulfillment service needs to know their address, so they call the customer service to get the customer's address. This works, but there might be operational reasons why this might overload the customer service, or we might want to be able to send packages even when the customer service is down. And so leveraging services and events, we can build a more reliable overall capability. So here I'll call this asynchronous event and local cache. So in this example, the customer service is anytime somebody's address changes, it produces an event which is then consumed by the fulfillment service, and then the fulfillment service is caching that the current customer address. And so anytime we need to send a package to somebody, the fulfillment service can use its local copy. How do we deal with joins in large-scale service ecosystems? So the first example, the simple one, is just simply joining in whatever the client is, right? So in this example, we want to build some order history, and we want to get some data from the customer service, and we want to get some data from the order service. And so we could simply have the order history service, call the customer service on the one hand and call the order service on the other hand. This works perfectly legitimately, but sometimes that join is too expensive to do in real time, or again, there might be other operational reasons why we want to be able to show the order history without the customer service or the order service being up, be more resilient to potential failures. And so the way that we can do that with services and events is having a service that materializes the view, right? So there's a service here that's listening to events from service A and service B and maintaining in local storage the join between A and B, and maintains that in a denormalized way. And so then that materialized view can be available to be queried directly as opposed to joining the two individual sides of it. Okay, so the last of these tools, these kind of combined tools I want to talk about is transactions. So if we had a monolithic database, which we absolutely do not at Google and eBay and Amazon and Netflix scale, but if we did, transactions are really easy. We would just write a transaction in our single database. We would join, or we would transact over the tables, two different disparate tables, and everything would work. But once we've split the data out into services, which we've done for scale and for simplicity, it makes transactions challenging. And so I love this quote from Pat Helland, who wrote this amazing paper back in 2007 called Life After Distributed Transactions. So in general, application developers at large scale do not implement large scale applications assuming distributed transactions. Or he's very funny and likes to say things very quickly. Grown-ups don't use distributed transactions. Okay, well, what do they use? The way to think about building these kind of capabilities at large scale is actually through a workflow, or what we'll call a saga. So instead of thinking about it as a transaction of several different entities that all happen atomically, think about modeling that transaction as a state machine of successive atomic events. So we're going to re-implement this thing as a workflow or a state machine. So instead of doing A and B and C transactionally, which we can't if they're all stored in separate services, instead we make the change to A. That produces some set of events which are consumed by B. B makes its local set of changes. It produces one or more events, and that's consumed by C, which again makes local changes. And if anything goes wrong along that path, the way that we deal with it is we actually produce compensating transactions or compensating operations in the reverse direction. So we sort of undo or revert the change to C. That in turn causes some reversion in B, which in turn causes some reversion in A. So one of the other things and many real-world systems, work like this. So payment processing works like this, right? So I would love it if somebody could pay me in an electronic way and the money would show up in my account immediately. That's actually not what happens. There's no distributed transaction between my bank and my collaborator's bank. Instead, it's a workflow that with a bunch of different atomic steps, again, through a state machine like this. Expense approvals work in a similar way. So a bunch of us who traveled here would go home to our companies and get approval for particular expenses. Again, that does not happen atomically and immediately. There's a whole workflow and process associated with those things. The end of which is probably going to generate a payment processing workflow. And then the software development process itself. So I'm sure there are a bunch of fans of continuous delivery in the audience, but raise your hand if every time you hit return in your IDE, everything is immediately and atomically shipped to production. Let the record show that no hands went up and there were some chuckles. So again, the software development process, the thing that we do as our day-to-day job, is also one of these workflows. And so when we implement these things as sagas, what we see is that we're actually we actually see these intermediate states. And the way I like to think about it is we should expose those intermediate states in the interface that we offer to our customers. So we should let them know that, okay, the payment is in the started state, in the pending state, in the complete state, and expenses may be submitted, then approved, then paid. And a feature, if we wanted to have some kind of feature service, it's developed, it's reviewed, it's deployed, it's released. Okay, so now that we have a bunch of these, now that we've put a bunch of these service and event architectural tools together, now let's talk about some real-world examples, and then we can go to questions. So I want to talk about 3 of them, and the first one, actually following along the transaction example, is pretty interesting. So Amazon Aurora is a distributed database, obviously offered by Amazon Web Services, and it's a distributed database, but it does not use distributed transactions internally. Instead, it does the things that we were talking about earlier. It uses asynchrony, it uses events, it uses immutable logs. And so if you're familiar with the internals of databases, the redo log is essentially the transactional stuff that's happened in the database. So like that's critical to get right and critical to be consistent. But instead of like writing to its redo log in a transactional way across the different distributed nodes in an Aurora cluster, instead those redo log writes are distributed asynchronously to those storage nodes. They're acknowledged asynchronously, and there's no distributed consensus. There's no distributed transaction happening there. Instead, the event exchange that's happening is idempotent. Everything is stored immutably, and the events move forward, the states move forward in a monotonic way. And so instead of having these, a consensus round, instead they do quorum acknowledgement. So when a quorum of the storage nodes respond back and said, hey, I've seen that redo log write, only then is the redo log progressed forward. And the only time that they run any kind of consistency around here is actually when they have a crash and they need to kind of bring all the storage nodes up and kind of figure out what happened. So this is pretty interesting that we're like a distributed database itself isn't using distributed transactions. The second case study that I want to talk about is a relatively recent one from Netflix. So the example here is Netflix viewing history. So the use case here is they're getting about 1 million requests per second from all of us who are watching Netflix, and they want to process those viewing events, and they use it for showing us our viewing history. They use it for personalization, for recommendation, for analytics, for a bunch of different things. Originally, there was a synchronous architecture where directly from your device, it would go synchronously all the way to the storage. But as you can imagine, like if there was any issue or blip anywhere along the line, they would have availability issues and potentially data loss of this data at high load. And so they re-implemented it in an asynchronous way, again, from that synchronous call graph to an asynchronous mechanism that I was talking about earlier. So instead, when the log event comes in, it gets written to a durable queue. Then there's an asynchronous pipeline that processes that queue of events, enriches it, processes it, stores it, serves it up later, and then they use the materialized view technique that I was talking about earlier to serve the read. So the way that you see your viewing history now is through one of those materialized views that we were talking about. Okay, the last and maybe most interesting case study here is a couple of years ago where Walmart rebuilt its item availability capability. So what is item availability? So when you go to the Walmart site, this is answering the question, is this particular item available to ship to this person within a reasonable time? Because it's online retail, the SLO that they were targeting for getting that response back to the customer was 99.98% uptime and a response within 300 milliseconds. And as you might imagine, if you know anything about retail, or even if you don't, there was a huge amount of complex logic that was associated with trying to figure out what warehouses is it in? Is it on the floor? How far are those warehouses away? Are there back orders on this thing? Are there reservations for it? Is it eligible for this thing or that thing? So there were tons and tons of different aspects of complex logic that were involved in making this item availability decision. And the original synchronous architecture, which I'll show you on the next slide, was a graph of 23 nested synchronous service calls, all of which needed to succeed in order to get that item availability answer. A failure on any one of those things would invalidate the results. And if you do the kind of availability math, in order to get that 99.98% uptime in 300 milliseconds, each one of those 23 services needed to have 5 nines of reliability and up to 50 milliseconds marginal latency. So it was an extremely expensive system to build, an extremely expensive system to maintain. And this is what the kind of architecture diagram looked like. It's not really meant to be looked at or perceived, interpreted by humans. And it's not the details aren't important, except there's just a lot of red lines. That's what you should take away. And those red lines are the hot path. So those are the 23 things, all that have to happen in order for that one answer of item availability to be returned. So instead what they did is they did that asynchronous inversion that I was talking about. So they inverted each service to leverage asynchronous events rather than those synchronous calls. So that it was an event-driven data flow that flowed up rather than sort of down. Each one of those services was idempotently processing the events that came in. Each one stored those events and its own data in an event-sourced immutable log. Each one of them was maintaining a materialized view of the data that it had, joined together with the data that it was getting from the kind of its upstream dependencies. And with that asynchronous re-architecture, there were only 2 services in that synchronous hot path. And the asynchronous services were able to have a much more relaxed service level objective because the updates to the physical updates to things moving in and out of the warehouses happened on seconds or minutes rather than on milliseconds. The overall system was much more resilient to delays and outages, and it was orders of magnitude, millions upon millions of dollars, orders of magnitude simpler to build and operate and cheaper. And so the architecture diagram there looked like this. And again, the interesting thing is just these two parts of the synchronous call graph. So a substantial, orders of magnitude improvement in simplicity and resilience by re-implementing this thing in an asynchronous way. OK, we made it. So we talked about simple components. We talked about simple interactions between those components. We talked about simple changes. And we put them all together with some combined architecture tools and some case studies. I do appreciate that I'm between you and beer. So I want to thank you very much. And thanks very much. I hope you had a great conference.
So while the beer is waiting out there, we do have time for maybe 2 questions, so I'm on my way.
Thanks so much for that. You briefly touched today and also mentioned yesterday about using sort of an ETL pattern for a lot of the reporting out of this.
Yeah.
Have you had any success with using an event stream to build reporting as well, like having a service that subscribes to all the events and building a report model from that, or is it a nice in concept but fails in practice kind of thing?
Oh no, it's totally legitimate in concept. Yeah, the question yesterday was about reporting, but yeah. So there are lots of different ways of getting data out of operational systems into analytic systems, and an event-driven way where if you have a stream of events, it can be consumed by operational systems, it can be consumed by analytic systems. That works fantastically. Or you also have the kind of standard, more kind of bulk ETL pattern. Yeah.
Awesome. Thank you.
Yeah, sure.
One more.
Hi. You touched on the importance of testing your system.
Yeah.
But in a complex event-driven system, how do you do anything more than a unit test? Do you have some experience testing effect that depend on an event being received by another system that received that event from another system? It's very difficult to test those cross-system effects in an integration sort of level.
Yeah, I see. I definitely see why you say that. Actually, I've found asynchronous event-driven systems easier to test, exactly because you can. I wouldn't call it a unit test, but I would call it a test at a component or a service level. And you say it really well, which is what happens in my service when I receive this event? Do I produce the events and the data changes that I expect? And the ability to, having systems that are asynchronous, actually I think it makes it easier to test those individual components of the service in isolation. You can always, there's always the, like you say, doing kind of end-to-end or integration tests, and that's always a tool that we have in our testing toolbox. But that gets harder and harder at large scale. Like you can't simulate all of Google, for example. Yeah, so actually, my experience has been that in an event-driven model, that it's actually easier and more effective to test the components independent of each other because they are more independent of each other, if that makes sense.
All right, I think it's time for the farewell reception. So if you have any more questions for Randy, then you can talk to him outside. Once again, can we thank Randy?
Thank you.